Alveolar ventilation is really important because that is the actual air that can participate in gas exchange from the lungs to the bloodstream and then eventually down to the muscle. Now, alveolar ventilation is harder to measure, much harder than minute ventilation. Remember, minute ventilation was just a product of tidal volume and breathing frequency. Both of those can be easily measured. Alveolar ventilation is just the volume of air that reaches the alveoli, and it's a V dot A. So again, it's a rate of airflow. So it's a per minute unit. It's in milliliters per minute or in liters per minute. Now, what do I mean by that reaches the alveoli? When you look at the anatomy of the lungs, of the airways in the alveoli, at the top we have the trachea, and then it splits into the bronchi, and then those split down into the bronchioles, and eventually you get down to the alveoli. Now, everything up top in that blue area, the conducting zone, all of that air is locked in the airways. There's no escaping the airways because of the thick walls and the cartilage that is surrounding those airways. It's not until we get down into the respiratory zones where we actually see some of those alveoli popping up. And once we have alveoli, that's where we can have gas exchange of oxygen and carbon dioxide going from the alveoli into the blood. So everything in the conducting zone is literally just air moving in and out from the atmosphere to the alveoli, but it's just a mass transit of the air. There's no exchange of air between the lungs and the bloodstream. So that is what is called dead space, and it's more specifically anatomic dead space. So the alveolar ventilation is just the air that is down in the alveoli, in the respiratory zones of the lungs. So it depends then on the dead space and the total minute ventilation. The equation for alveolar ventilation is minute ventilation minus dead space ventilation. Or, because minute ventilation can also be broken down into breathing frequency and tidal volume, another equation that we can use is alveolar ventilation equals breathing frequency times the difference between tidal volume versus dead space volume. We have a pretty good estimate of how much this volume is, and it's about 150 milliliters in an adult person. A normal resting tidal volume is about 500 milliliters. If you distract dead space volume of 150 milliliters from the resting tidal volume, we have about 350 milliliters that actually make it down into the respiratory zones, into the alveolar space. The rest is maintained or is stuck in the conducting zone, and that's the first air that is actually being breathed out again. So let's put all of these concepts of respiratory volumes and respiratory flows into a picture form. We're going to have some lungs up here with the trachea, and then a big representation of the lungs right here. And then we have pulmonary blood flow coming in from here. Okay, so up top we have the trachea and the upper bronchioles, and then all the way down into the airways and the alveoli and the respiratory zones. At the bottom we have the pulmonary capillary or pulmonary blood flow coming from the heart into the lungs, picking up oxygen, dropping off carbon dioxide, and then returning back. So we have blood flow coming in here and going out here. We're going to have volumes on the left side, and we're going to look at flows, air flows on the right side. So we have air coming in and out of the lungs, normal tidal volume at rest, tidal volume is about 500 mils. And we said dead space volume, or the volume in the upper airways, right around here, is dead space volume. And we said that is estimated to be about 150 milliliters. So over here on the right side, we're going to put flow. Minute ventilation was the product of tidal volume and breathing frequency. So at rest, breathing frequency is normally between 12 and 15 breaths per minute. Let's call it 15 breaths per minute. So 15 times 500 milliliters, and we are at approximately 7,500 milliliters per minute, or 7.5 liters per minute. Now, what is dead space ventilation? Dead space ventilation is the breathing frequency times the dead space volume. So breathing frequency, again, let's call it 15 breaths per minute. The dead space volume was 150 milliliters. So now we're at 2,250 milliliters per minute. Alveolar volume is then the volume of air that makes it down into the respiratory zone. So that would be the difference between tidal volume and dead space volume. So 500 minus 150 milliliters is 350 mils. That's the volume that actually makes it down into the alveolar. So what is then alveolar ventilation? Well, there's two ways of doing it. What we've done with minute ventilation, we can do that. So it would be minute ventilation minus dead space ventilation, or 7,500 minus 2,250 milliliters per minute. So we can do VE minus V dot D. And that gives us 5,250 mils per minute. Or we can do alveolar volume times breathing frequency. And that gives us exactly the same thing. So the alveolar ventilation is the volume, again, the volume of air that can participate in gas exchange down here from the lungs into the bloodstream. And one more note to make here, normal blood flow at rest is approximately 5,000 milliliters per minute. And you see that that is very close to alveolar ventilation. So we have very good matching of the air that is actually participating in gas exchange with the blood flow. Now let's take a look at what happens during exercise with alveolar ventilation in our volumes and flows. Again, I'm going to start up here with the trachea and bronchi, and then a representation of the lungs. And we have pulmonary blood flow coming in and going out. So we have blood flow in and out, and we want to have gas exchange between the alveoli and the blood flow. That's our ultimate goal. Now during exercise, let's say my tidal volume has increased to 3,000 milliliters. And breathing frequency, let's say, has increased to 40 breaths per minute. That means my V dot E, my minute ventilation, is tidal volume times breathing frequency. So 3,000 milliliters times 40 breaths per minute gives me 120. And let's use liters per minute as the units here. Now, what's the dead space volume? Well, dead space volume, again, volume that is stuck in the trachea and the bronchi, that is still 150 milliliters. So VD is still 150 milliliters. So dead space ventilation is now 150 mils times 40 breaths per minute, or 6 liters per minute. The V dot A, the alveolar ventilation, is VE minus VD, or 114 liters per minute. So let's put this all back together. For minute ventilation, remember the equation is tidal volume times breathing frequency. So at rest, a normal tidal volume is about half a liter. Normal breathing frequency is about 12 breaths per minute. So 0.5 times 12, we get a minute ventilation of 6 liters per minute. Now during exercise, let's say moderate exercise, tidal volume has increased to about 2 liters per breath. Breathing frequency has increased to 30 breaths per minute. And now we have a minute ventilation of 60 liters a minute, a tenfold increase from resting conditions. Let's take it one step further. During intense exercise, the tidal volume can go up to 3 liters per breath, breathing frequency of 40 breaths per minute. And now you see a minute ventilation is up to 120 liters a minute. That's 20 times the resting condition. So we have a large respiratory response during exercise. Now, what happens during exercise training, endurance exercise training? We said that all of these variables are increased. Tidal volume is increased at max, breathing frequency at max is increased. So it follows that minute ventilation is also increased. But there are no actual structural changes that occur in the lung due to training. But the improvements that we see, or the higher ventilation that we see, is mainly due to efficiency of the respiratory system and better trained or stronger respiratory muscles. So what we could see in the endurance trained individual is a tidal volume of 3.5 liters per breath, 45 breaths per minute, and a minute ventilation of over 150 liters per minute.